Hey y'all, welcome to another math video. We'll be discussing a topic in quantum science, the Bloch sphere and complex projective space. And really, the Bloch sphere as a case of complex projective space, where we will define CP and complex projective space and use the specific example of the Bloch sphere for spinors, which maps some psi equal to alpha beta to what we call a 2-sphere or a 3D sphere. And that does that by going from C2 to CP1 to S2. Okay. Okay. We define a complex projective space as complex projective space maps an n+1 vector space to an n-dimensional rays. And they're rays because the vector x will be exactly equivalent to a dimensional space, to lambda x in CPN. And we'll show that's true. So for example, let's take some space with the set u1, u2, u3, un+1, and then map each v equals v1, for example, equals u2 over u1. Or u2 over u1, the I phi, which equals basically un+1 Rn un. So this is n+1 dimensional, and this is n dimensional. How is that useful? We'll see exactly how that's useful with the Bloch sphere. So we have a general space that takes n+1 set of vectors, maps it to an n-dimensional space. And you'll see, for example, if you have lambda u2 over lambda u1, which are two distinct vectors in the original space, equals u2 over u1. So they will be completely not distinct. Sorry for lambda. They'll be equivalent in complex projective space. So now let's take, for example, C2 to CP1, where we have our psi equals alpha u1 plus beta u2, which means we can call it R equals alpha over beta, or alpha over beta u2 semi phi, where we can find the argument, but we don't have to do that right now. We can find phi with algebra. Not really necessary right now. And now we can map our R's to a 3 sphere. Sorry, a 3D 2 sphere. That's the fancy way to say it. And the way we do that is you place, so each R is a point on the unit, no, it's not, sorry, not unit, on the complex plane. C1. So we're actually, the CP1 can be interpreted as either R2 or C1. Okay. So for example, I just call this X, Y, and here is R. Okay. And to center unit sphere, on the origin. So let's call this our XY plane, this our Z, this, oh, that's supposed to be a circle, okay, this is our unit sphere. Then 3, draw intersection from South Pole to point R. So we had R here, for example. We draw this, and the intersection points are here and here. Okay. And then our unit vector from origin to intersection equals our vector in S2. So our vector in S2 will be this, S2. Okay, which means we have any number of points. For example, we can have an R2 here, and this is just along, it's a 2D drawing. We can draw it also like this. Here we have X, Y. Let's say we have a point here. So the drawing will come out and intersect the sphere. Okay? I don't know how to better visualize it. But that's how we map from this maps maps an xy point to a 3-sphere. Now let's take some limits. Now we need to do single point compactification. Now we can close this by defining a limit. So if I draw this drawing again, let me just copy it. If I draw this drawing again, so you can see as u2 over u1 goes to 0, red will point to north. And as u2 over u1 goes to infinity, let's say we have a point root 4 here, the intersection will be right here. Red approaches south, but it's not defined. So if we define the limit as u1 to u1 goes to infinity, as the vector going straight down, we make the mapping compact. And that's called single point compactification. And that is single point compactification. And phi just basically rotates. So phi basically just rotates along the sphere. R is what defines this direction. It's perfectly symmetrical to R. And this sphere, so this 2-sphere is our Bloch sphere, where we take some state in C2 and we map to a 3D sphere. And that's mathematically how it works. Some formulas that will take too long to derive. Basically, we have let me look at the formulas. Sorry. R theta phi. So if we go from sorry, let's just go theta phi. Theta phi. So on a unit circle, on a unit sphere, sorry, on a unit sphere, on a unit sphere, if this is the z, then this, at least for physicists, is theta, and then this xy is phi. Phi is the azimuth. Oh, I screwed up. No. Wait. Yes. Yes. That's the azimuth. And then this is called the zenith. And then so we go from alpha 0 to beta 1 to theta phi.